second speaker is Dr. Naika. He's from the National University of Singapore to report on an international effort that explicitly looks at humidity, introduces ideas of urban dry and moist islands.
Okay, hi everyone, I'm Naika and I welcome you to my presentation today in which I will quantify humidity changes in cities at the global level with a global data set. Well, first of all, why do we even care about humidity changes in cities? Well, similarly to high temperatures, high humidity can have serious implications for heat stress or mortality worldwide. For example, here on the right-hand side, I show you a map of the projected heat stress days or number of heat stress days under climate change. And as you can see, especially in the hot and humid regions of our world, in the tropics, we will likely experience a large number of these dangerous heat stress days. On the other hand, there has also been recent literature looking at the effects of humidity in predicting electricity demand for building cooling and have found that if we are not considering humidity, we might actually underpredict the peak electricity demand. So what do we know from past literature on humidity changes in cities? Well, past literature has mostly focused on measurement studies of single cities or single urbanizing regions. When we're looking at humidity changes in cities, we can look at this in terms of changes in relative humidity measures, such as relative humidity or vapor pressure deficit. And we can also look at changes in so-called absolute humidity in cities, such as, for example, specific humidity or vapor pressure. And what we can see from past studies that the results are non-conclusive. There are some cities that show an urban dry island when measured in terms of absolute humidity, so less humidity in cities than their natural surroundings. There are some cities that show an urban dry island only measured in terms of relative humidity measures. However, they don't show an apparent change in absolute humidity or non-conclusive change in that. And then we even have some cities that show an urban moisture island when measured in absolute humidity terms, meaning higher moisture in cities than their natural surroundings. However, in this study, I would like to know now what is the dominant pattern of these humidity changes or these so-called urban dry islands at the global level. To do so, I'm using a meteorological data set of globally distributed stations, and I will answer the following research questions in this talk. First of all, what is the global average diurnal and seasonal pattern of urban dry islands? Are there any differences in these patterns between relative and absolute urban dry islands? And to what extent is the relative urban dry island actually caused by changes in temperature, such as urban heat island, and to what extent in changes in humidity? To quantify this global urban dry island average, we're using a space for time substitution, which I will explain now in the following. To do this space for time substitution, we're leveraging the fact that many cities or regions of this world have experienced actually very rapid urbanization in the past 3 decades. I show you here the example of Toulouse in France and Shanghai in China, and these black dots here represent meteorological stations. And you can see how these stations experienced very rapid urbanization in the past 3 decades. Stations such as these will have a climate trend, or they will measure a climate trend, which is partially obviously influenced by climate change, but then also another part of the climate trend is attributed to the development of an urban heat or an urban dry island. We then also can assume if this urbanization is happening more quickly, the development of urban heat island and urban dry islands are likely also more quickly. So what we can now do is that we take a large number of meteorological stations distributed globally, and we correlate their climate trends measured in temperature and humidity with their urbanization rates. So we have stations that have no urbanization, and we have stations with urbanizations. And what we see when we are correlating these stations or these trends, and we fit a linear regression, the slope of this linear regression would give us the expected urban dry island or urban heat island, which we would expect to develop at 100% urbanization around this station. The intercept would represent the climate change effect or is representing the climate change effect. However, since our stations are non-uniformly distributed across the globe, so like rural and urbanizing stations are not paired up, but they can have slightly different distributions, we remove the climate change effect beforehand with ERA 5. So in the following, when I show you these correlation graphs, you will see an intercept very close to 0, and this is just because we removed the climate change effect beforehand. So with this method, we're quantifying the urban heat island measured in terms of near surface air temperature, relative urban dry islands measured in terms of relative humidity, and absolute urban dry islands measured in terms of specific humidity and vapor pressure. As I quickly introduced, we're using a data set of many globally distributed meteorological stations. This data set initially had roughly 8,000 stations. However, we applied some quality control, and we also only selected stations which had at least 3 hourly data frequency during the analysis time period, which is from 1990 to 2018. So this left us, after this quality control and ensuring the consistency of the data, this left us with roughly a bit more than 1,000 stations. Also, roughly of these 1,000 stations, roughly half of them are experiencing some urbanization versus half of them have very negligible urbanization. We then also calculated the urbanization rate, meaning the change in land cover to artificial impervious land cover within a radius of 7 kilometers around this station. We tested the assumption of this 7-kilometer radius, and it was non-critical in our results in the end. So with all of these stations, we have the urbanization rate and we have the climate trend, so we can do now this correlation analysis. And I'll show you here this first for air temperature. And I know there's a lot of information on this graph, but what I would like you to focus on is this particular number here. This particular number is the annual average urban heat island across all of these stations, which we would expect at the formation of, or at the land cover conversion to 100% impervious land cover. And as you can see, this number is very small, and it's actually not statistically significant. However, when we're looking at absolute urban dry island measured in vapor pressure and relative urban dry island measured in terms of relative humidity, we find that both for absolute and relative urban dry island, there is a statistically significant urban dry island present at the global annual average. But I promised you beforehand to look at the diurnal and the seasonal patterns. So let's do that. So for the urban heat island, this is the summer month average, the diurnal cycle. And what we can see is that for the urban heat island, we get the expected temporal pattern. We get urban heat island during nighttime and negligible to non-existent urban heat island during daytime. I would like to mention that the solid bars are representing statistically significant results versus the slightly transparent bars are not statistically significant results. When we're looking now at absolute and relative urban dry island, we can see that they have different diurnal patterns. The absolute urban dry island is largest during daytime and the early evening hour, versus the relative urban dry island is largest during nighttime. So when we're looking at the relative urban dry island now at the diurnal cycle, how much of it is actually caused by a change in temperature, so urban heat island, and these higher temperatures can lead to an increase in the saturation vapor pressure, and how much is actually caused by an actual change in vapor pressure in the air. And so this is shown here in the graph on the right-hand side, which shows the vapor pressure urban dry island. And what we can see is that the vapor pressure urban dry island is mostly caused by changes in vapor pressure or absolute humidity in the air during daytime, and it's exacerbated by urban heat island at night, so the change in saturation vapor pressure. At the seasonal scale, we see that both absolute urban dry island as well as relative urban dry island for day and nighttime are largest during the warm season of the year or the summer months. We also find that the urban heat island is largest during the warm season for nighttime. Okay, with this, I'm already at the end of my presentation, and I quickly would like to share the take-home messages. Well, first of all, we have applied a space for time substitution here, leveraging the fact that many of the meteorological stations actually experience rapid urbanization in their surrounding. And with this space for time substitution, we can quantify the global average urban dry island. We have then found that at the global annual average, there is a relative as well as an absolute urban dry island present. We found, though, that the absolute and relative urban dry islands have different diurnal patterns. Absolute urban dry island is largest during daytime versus relative urban dry island is largest during nighttime due to the urban heat island effect on it. And then lastly, on the seasonal level, absolute and relative urban dry island are largest during the warm season. With this, I thank you for your attention, and I'm happy to answer your question. And if you would like to know more, these results have already been published, and you can look at the following article.
Thank you very much.